then let's get going. So thank you all for coming here. This is going to be an about 45-minute presentation on motion in MRI, and I've subtitled this "A Gallop Through the Mire." A gallop because we're going to be relatively fast, considering how big of a topic this is, and through the mire because you know, everything moves unless you're doing postmortem, and there are many facets to the interactions of motion and MRI, and there's no silver bullet, so it's quite a bit of a quagmire to sort out. So what we'll be talking about, I'll tell you what I think is a good explanation for what motion is. I'll talk about the primary impacts of motion, which is the interaction between your motion and your k-space. I'll talk about the secondary impacts, how we might mitigate motion. And then once we've done some mitigation, okay, we need to measure what is left, and then hopefully we can correct it. Then I'll finish with some excursions into deep learning. That's where sort of my expertise will completely end. So that's just a couple of slides. But with that, let's get going, or moving, should I rather say. So what is motion? Here I've taken the definition that it's any displacement of the image tissue that is not deliberate by the person doing the imaging, just so people who have ever done elastography or something like that don't. So that's not, elastography and other things like that aren't considered part of this talk. And whatever motion we have, we can categorize it in many ways. And any motion you have will fall into some of these categories or some other category that you can come up with. So it can be something that's voluntary, something that's involuntary, something that's physiological, it can be occasional, it can be constant, it can be periodic, it can be random, it can be large, it can be small, it can be preventable, it can be not preventable, it could be correctable, etc. So for example, if you have somebody in there with a movement disorder and they do a jerk, that's something that's involuntary, occasional, random, usually large, ideally preventable, but hopefully correctable. If you have, for example, heartbeat, then you will have a physiological, constant, periodic, small, and most of the time not correctable flow artifact somewhere in your image. And then basically any motion you can come up with will fall somewhere between those two extremes. Okay, so how will this motion affect our image? And the main way in which it interacts with our image will be via k-space, and we have to do somewhat of a deep dive into k-space and MRI encoding here. Because in MRI, we are not exactly acquiring an image in the sense that we're not taking a photo. It's not a signal intensity location pair like you would take with a normal camera, but we acquire k-space, which is a set of spatial frequency amplitude pairs. So what we do is we encode some data in our k-space and then we read it out. And then to acquire our whole image, we fill up this k-space sequentially and we move within this k-space using gradients. So it's quite different from how you would acquire, for example, a photo. And because of that, the impact of motion is also markedly different. So I'm sorry, but we have to somewhat go into the depths of k-space. So as a refresher, k-space is a collection of spatial frequencies. So it's nothing more than points that encode how many of what variation of these waves of bright and dark you need to take to generate your image. You have your image in real space, and then you effectively decompose it into these waves. And if you take enough of them, then what you will end up with is your reconstructed image if you fill up the whole of k-space. And the resolution and field of view in your image space are intimately tied to things in k-space and vice versa. What this means is that your field of view in image space is related to the spacing in k-space, e.g., how big the steps are between one wave pattern and then the next wave pattern that you encode. And conversely, your resolution or your delta x depends on how far out in k-space you go. You can imagine that if you want to encode something that's a really, really small variation in image space, then you need to put a lot of these wave patterns together to get it. A couple of other properties of k-space that will impact us. One is k-space energy, and that's just how much the intensity here is. And related to that is the very important fact that because each k-space point encodes a wave pattern, each k-space point corresponds to all, contributes to all of your image. So if something happens in just a single k-space point, your whole image is going to be affected by it. So next thing to talk about is how we go through k-space. You can separate this into an instant, a fast, and a slow encoding direction. And in this case, we go through k-space, for example, by reading out a line, collecting an echo, or moving through frequency encoding. Those are equivalent things. And then we step up using phase encoding. So we acquire all of this data, zip, in 2-3 milliseconds, in the time it takes us to collect an echo. And then we move up one phase encoded direction, zip again, move up, zip, etc. And each of these moves is slow compared to the readout, but this is still our fast phase encoding direction because there's only one of these steps between each TR. Now, if this was a 3D case, then we have an additional plane, going through the monitor effectively, and that's on slow phase encoding direction because we need to fill up all of this k-space before we move up to a next k-space plane, which means that these directions are differently sensitive to motion. And we usually think the usual wisdom is that this readout direction is instant. You just go through it. It's not sensitive to motion. And then the fast encoding direction, so this is less sensitive, and the slow encoding direction, which would be through plane here, is the most sensitive. Almost done with k-space refresher. Two important things yet to cover. One is the Fourier shift and Fourier rotation theorem. These just mean that a translation in real space is a phase offset in k-space. The easiest way to think about that, hello, animation, yes, thank you, is that a translation will change the k-space energy. It will either add or remove some phase to that k-space line. If you do the magnitude transformation, then the magnitude will change. Conversely, the rotation means that the rotation in real space is a rotation in k-space, which will displace this energy. So this was here, now it's here, it has been displaced. And related to that is the so-called Nyquist criterion. Remember back that our field of view is determined by our spacing in the k-space, how big these steps are. So now, originally, we had steps that are this big, and here we have a step that's twice as big. We have a field of view that's half as big, which will result in fold over. So the end result of all of this is that if you have motion, you will have a displacement and a change in k-space energy compared to your uncorrupted image. And the end result of this are artifacts that we tend to call ghosting and blurring, but they all impact your image quality in a fairly negative way. How these look like is, for example, here is the eye artifact. This is a involuntary, periodic, and uncorrectable motion because even if you close your eyes, you are still going to stackate there. You are still going to move your eyeballs, and the motion of the eyeballs is displaced either out of or into the tissue of interest, depending on how you do your phase encoding. So, ghosting. Or this is from really high resolution in vivo data. And you can see that there are these ugly looking waves and lines here, and the border of the salsa and gyri has been sort of blurred away. That's fairly typical of a motion artifact as well. Or what you might see are these ringing artifacts, which are fairly characteristic of motion as well. So there's a couple of rings here, a couple of rings here. And you can see that a lot of this information has been sort of ghosted out into the signal void. Apologies. And to see what the difference is, this is a really nice data set where you have a motion corrupted image, and then you do your retrospective motion correction. And the difference between the two is obviously what the motion artifacts look like. So motion artifacts will look something like this. They are either these ugly wave-like things corrupting your image, or there's something a bit more subtle that will make things blurry. But the end result is that motion artifacts just make your image look less sharp and less interpretable than if they weren't there. Okay, so let's move on to the secondary effects. And there's a couple of those. The first one I want to mention is that what we do in MRI is we put a lot of work into having our B node field be exactly what we want it to be at exactly the position where we want it to be. That's how we do our encoding. And then we put a human being into that. And because human beings are not isotropic spheres, this B node field gets distorted. However, if they move, then these distortions move as well. And the end result of that is that, and you can see that if there's motion, in this case, nodding, then the resulting fields are different. I hope this comes across well on your screen, but this distortion here is different from this distortion here. This distortion here is different from this distortion, etc., etc. The end result of this is that even if you do your motion correction for the primary effects, for the effects of K-space immaculately, then you will still have the signal distortion and signal dropout that is caused by these secondary effects, this motion in B0. There are ways to correct for that, but I'm not going to go too much in depth. And because we're a spinal cord imaging lab, the shimming of the spinal cord that you need to do to counteract the effect of breathing falls effectively into this category of a secondary effect of motion, that there's a breathing somewhere, and somewhere else the field has changed that you now need to take into account. Another secondary effect is what I like to call, what is called spin history. Spin history is just what has happened to the tissue from excitation to data collection. And if your image tissue moves between excitation and data collection, then you have a spin history effect. The illustration of this can be seen here. So you have 3 pulses, and to get your data, ideally you want no motion between them. If there is motion, then what you think is one well-defined slab is going to turn into this rather badly defined mix. And I think the best example, and the one that most of us will encounter during our sort of daily MRI lives, are flow artifacts, e.g. blood is flowing in or out of the tissue of interest, and it will either add signal that you don't want to be there, or subtract signal that you want to be there. In this case, you can see that the flow of blood here and here and here and here has caused motion artifacts, has caused extra signal, has caused extra K-space energy that has been displaced into the tissue of interest. It's an artifact. Lastly, I want to mention the effect of motion on the receiver and the transmitter fields. This is from my thesis. This is the secondary effect of motion and the effect of inter-scan motion. So if you have two scans that you want to co-register and do something with, head is here, then the head is here. And the underlying anatomy obviously isn't changing. Even if this was two completely rigid, unmoving postmortem samples, the fact that you've moved them around in the receiver field, in this C, means that the resulting image will look different. So the way to counteract this is, in this case, to map the receiver field for each position and then divide it out. Another way in which the receive field and motion interact are the ACS or auto calibration lines when you do undersampled or accelerated imaging. So what's going on in GRAPPA or in SENSE is that we take a central portion of the K-space and use that to calibrate our receiver sensitivities, and using that calibration, we can then fill in the lines that we skip using parallel imaging. But if there is motion between when you do your ACS lines and when you do your undersampling, that will have an effect. This is a relatively understudied part of motion and motion correction, but there's a couple of publications that have looked at it. Here you can see the effect of it on fMRI, or you can see that if you use, for example, the ACS lines from a motion corrupted case to interpolate the lines from a motion uncorrupted case, you sort of inherit that motion corruption and vice versa. So this is fairly, I think this is fairly impactful, but sadly understudied. And lastly, for transmitter fields, this is more important for PTX, which is that you can have your nice pulse design on PTX that makes everything, as good as you want it to be, and then the person's head moves, and then your PTX pulse design isn't ideal anymore. And the higher your, in this case, your motion is, the worse your PTX pulse design is for that case. So these are the primary and secondary effects of motion. And I know that was quite dense. So if there's any questions now, please ask. Anyone?
Yeah, okay. So can you maybe go back to the head tilting slide you had?
Which one?
It was like the first slide you had where you had that animation.
This one?
So when you say, okay, what is the difference between changing K-space energy and displacing K-space energy?
So when you change K-space energy, then all of these lines stay where they should be. You just add or subtract.
Like they get more intense,
yes,
or less intense?
Yes.
Okay. And then this line on the right side, the line at an angle is supposed to be?
Yes, that's been rotated out of where it should be. Rotation in the real space is an equivalent rotation in K-space.
Okay.
And Daniel, just to be clear, so the single line that's being rotated is because we imagine that the person moved their head really fast and then came back.
Yes,
afterwards,
yes.
right?
That's what I wanted to illustrate here. These are the only two figures that I did. Everything else has been borrowed from publications, and you can see why. But yes, that's the idea, that the motion that is occurring during the acquisition of a k-space line will influence where that k-space energy goes. Yeah. I want to say that it changes k-space energy is sort of my interpretation of translation in the real space results in a phase role in k-space, which I always found fairly hard to understand. And I think changing k-space energy is effectively what it does, but I'm not 100% sure. It just makes sense to me in the way I interpret k-space and everything, but this is not an image reconstruction lecture, so I'm not going to go too much in depth. But I think the main takeaway is more this, is that motion basically puts k-space energy into places where it shouldn't be. And that's where all of these issues come from. That's why you get these wave patterns, that you get distortions, etc. Any more questions? No, then I'll move on to mitigating it. So, okay, motion will have an impact. Now, what can we do to make this impact less? Well, we can make it so that the people don't move that much, which is the somewhat traditional MRI pads we all know and love. These are basically just sponges, but they're really, really expensive. We can go a bit further and add on additional restraints to the patient. This also has the effect of making them not touch the ball, not cross their legs, not cross their arms, etc. Or if we go to one's neonatal imaging, then what's happening there is you feed them so they fall asleep, then you swaddle them really tight, and then you put them into a vacuum immobilizer, and you try to do this fast enough that they don't wake up. So mitigation is just a fancy word for telling them not to move. The training also falls into here, which I haven't mentioned. Next is we can choose our k-space trajectory smartly. You've seen this image already, but this just shows you that if, let's say this is a 2D image, if your phase encoding direction is right to left, then the motion sensitivity is effectively that direction. So here the artifact is displaced out of the tissue of interest. And if it's AP, then it's now displaced into the tissue of interest. And to show you the interactions between k-space trajectory, e.g. how you fill up your k-space, whether it's sort of sequential, whether it's center out, whether it's something esoteric, this is again from my thesis. So what's happening here is that we had a nice way of feeding the scanner a motion trajectory. So making this kind of thing that some motion has occurred. And we fed the same motion into 3 cases that have been acquired with different k-space trajectories, which is that the sensitive phase encoding direction was this direction here, and what's called a square spiral readout, which means that you step once in the first phase encoding direction, let's say ky, and then you step in kz, and then in ky, and then in kz, and you fill up k-space that way, which sort of disperses the apparent motion artifact into both directions. And you can argue which one looks better and which one looks worse, but you can see that even under the same motion trajectory, the resulting image is fairly different. And there's a special case of k-space trajectories, which are the radial k-space trajectories. So in radial trajectories, what we do is that we don't fill up our k-space sequentially like a box in so-called Cartesian imaging, but we acquire these lines such that they always go through k-space, which results in them looking like the spokes of a wheel in this radial fashion. And what's usually said is that they are less motion sensitive. What that means in effect is that the motion artifacts look less coherent. Like here, this is an abdominal scan very much affected by breathing, in this direction. This has been chosen as a phase encoding direction, and it looks unusable. If you have the same effect, but you acquire the data in a radial fashion, then it looks much sharper. But to push back a bit against the conventional wisdom that radial case-based trajectories are not affected by motion, that is not true. They are, but the artifacts are not this coherent displacement, this coherent ghosting of something on top of the image of your interest, which sort of renders this whole thing usable. But they are more these, I hope you can see these lines, these streaks sort of fanning out. That's more what motion looks like in a radial scan. And that's also an effect of just radial scanning in and of itself. So it's more that you're trading coherent ghosting artifacts for incoherent noise-like artifacts that don't impact your resolution, your effective resolution all that much. And you also get this blurring. I will mention radial trajectories a couple of times, and you might come away thinking that, oh, they are the magical solution to all of our problems. The reason they are not is that to get an equivalent field of view and signal to noise ratio, you have to spend pi/2, so about 150% of the time imaging that you would have to do with a Cartesian one. They have really cool properties, but they're not the magical solution to MRI and motion. And if there's one thing to take away from this talk, is that there is no magical solution to MRI. To motion in MRI. Last mitigation is gating, triggering, and binning. So these are all things to counteract physiological motion. And what we do is we measure it somehow. We'll just put that aside of how we measure motion. We just measure it. And then we either acquire our data only in a specific phase that would be triggering. So here we have this heartbeat, and then sometime after the heartbeat, we know that we need to acquire. So heartbeat, oh, enough time has enough, the trigger delay has expired. Now let's acquire our case space. We acquire some. Next heartbeat, we acquire some more. Next heartbeat, we acquire some more. Gating would be if we always acquired this data, but only kept some of this case-based data that corresponded to this phase. I must say here that triggering and gating are fuzzy concepts. They're not all that well delineated. So this separation is a bit more mine than the, fully adopted literature. You might see triggering and gating, and they more or less refer to the same thing. The whole idea is just that you have, a marker of, oh, heartbeat or breathing has occurred, and we are now in this specific phase, and that means we need to keep that data. The last is binning, in which case we acquire all of our data, and we have here a respiratory monitoring, and we just put our data into corresponding bins of like, this is fully inspired, this is fully expired, and then we just put whatever case space is into corresponding bins, and we reconstruct all of that. Binning is very useful because you don't waste any of your time, but it's also fairly computationally expensive. And for example, you can, so most of these examples come from abdominal or cardiac imaging because that's where you're most affected by it. People always breathe, people always have a heartbeat, hopefully. And you can get really nice looking cardiac, like this is, I think this is the short axis view images using, so this is ECG gating. So there's a little ECG on the person's finger, and that's what's happening, that's what's helping them trigger, and this is self-gating, which we'll come back to somehow, but this just means that it's fully MRI data-driven gating. Whew. Okay, enough about that. Any questions? No, then I'll move on. Oh, question? No. Okay. So fine, we've mitigated our motion, but now we need to measure whatever's left. So how do we measure motion? There's three bigger categories that I've chosen to impose on all the methods: navigators, optical trackers, and RF-based trackers. So what's a navigator? A navigator is an MRI-related signal that we can use to monitor motion. And depending on how we use this signal and this information, this can be a case-based navigator, an image-based navigator, or a receiver coil-based navigator, and whatever other categorization someone else can come up with. So what's a case? Okay, and the way they work is you need a sequence that has some kind of dead time. Dead time is where not encoding or reading out. For example, this is an inversion recovery, so we have our inversion pause, and then we wait for the inversion to go its thing, and then we read out. And I mean, while we're waiting, we're not doing anything with the sequence. We might as well chuck in something to tell us where the motion, what the motion state is. And that's a navigator. So case-based navigators are a 2 or 3D trajectory that is acquired in case-space for each TR, and that you then compare to a baseline, and you compute the motion in case-space. Remember, we have the Fourier shift and the Fourier rotation, and we can just in case-space compare our data to baseline and figure all of these things out. There's a couple of examples that are mentioned here in the references. What I'll show you now is the so-called cloverleaf navigator, because if you look at it from the top, it looks like a cloverleaf. And you can see the reason why these haven't taken the world by storm, which is that to properly play out this navigator, you need really good control over your gradients because you're always doing something funky. But if you have that level of control, you can turn this clinically useless garbage of an image into this clinically useful non-garbage of an image. But these have somewhat fallen by the wayside. I'm guessing mostly because of this here, that you need to play out these gradients really, really accurately to be able to do your navigation. The other option is to do this in image space, in which case the navigator data is reconstructed, co-registered to your baseline, and then you derive your motion information from that. There's, like with the case-based navigators, there's a million versions there. So for example, with case-based navigators, I mentioned 4 trajectories, but if a trajectory exists, a PhD student has made it into their thesis for case-based navigation, more or less. Same thing is true for image-based navigators, but these are good examples. So promo is a set of free projection to the images, like, for example, the localizer. So you can think of this as inserting a really, really quick localizer in front of each TR, and then based on that, co-registering it to the first localizer and getting your motion trajectories. This is the original promo paper, and this is the one where these images are taken from. So this has been successfully applied to children. You can see that these are not particularly clinically useful scans, like, you know, try doing a gray-white matter separation on this image. Virtually impossible, whereas here it's much better. That's basically what navigators do, is they turn useless scans into useful ones. You can also just quickly see that this is a spiral readout. So if you play on these gradients, what happens is you go into a spiral through case space. Next, are VNAVs or volumetric navigators. That's where I took this image from. So this is a 3D EPI that's always played out. 350 milliseconds is more than enough for a low-res, highly accelerated 3D API to be acquired. Then using that data, this is on a time-of-flight image. You can turn this, again, useless, undelineable, well, basically crap, into a fairly sharp image. The last thing I want to mention are FET navigators, which are a really cool idea, where previously the navigator and the imaging were on the same frequency. It was all hydrogen, it was all water imaging. But how about we do our navigator not on the water frequency, but on the FET frequency, because we don't care about the FET frequency anyway. So there's not going to be any problems if we mess up our water signal. And the end result are these fairly stark outlines of the head. That's where the fat is between your skull and your skin. You get your motion estimates. And then here on, I think this is 350 micron isotropic data, so really high resolution. You can get rid of this blurring here or this little artifact here. And it's really nice. They show all of the difference. So FET navigators have seen quite a lot of uptake. So have VNAVs, so has Promo. So these are fairly well-established methods. Last thing I want to mention are hybrid space navigators, which were technically the first ones to be developed. If you hear projection navigator or pencil beam navigator, these are functionally equivalent things. So what's happening here is that you shine a pencil beam through the image. So in MRI terms, you excite this thin slab here, this thin slab here. You look at this signal, and you do your Fourier transformation only in one direction. So you don't get an image, you get a 1D projection. Here, let's say this is the abdominal wall. And then what this tells you here is the signal intensity, the amount of k-space energy in that signal, and that will obviously correspond to, in our case, physiological motion, e.g. breathing. That's what pencil beam navigators are used for, is abdominal imaging and then breathing. And a really cool idea, and they were the first to be developed, I think. Okay, receive field navigators. As I've told you before, if you move within the receive field, and we can exploit that. The first publication, I think, is this binnir actual one, but what I'll show you are FID navigators. An FID, as a refresher, is nothing more than an excitation and then a completely unencoded data collection. So you just excite and you collect, and you don't play out any gradients. Now, the way you get spatial information is that we don't have one coil around the head. We have 32, 64, however many. And each of these coils will see the signal intensity differently. And if there's motion, then that signal intensity will now change. So here, this yellow one had a little bit of signal. Now it has a lot. And you can do your data collection and then tell, oh, motion has occurred. And FIDs have also seen fairly good uptake, and they work about as well, even on sort of not really motion corrupted data. Like there hasn't been any deliberate motion here, it's just people move. They work about as well as RF-based signals, but they require a lot less work. I've also dabbled in this. So this is a flash sequence. Flash sequences are really rapid MRI sequences with 0 dead time. So there's not really any time to insert a navigator because, as I've told you, you require some dead time. So what I did is there's always a big spoiler at the end of a flash to kill whatever signal is there. Why not a spoiler? Why not acquire some data at that time, because that should be instructive of motion in one way or the other. It turns out it works, but I'll be completely honest, it doesn't work that well. I do have a patent on it, but I haven't seen any money from that patent, if that's a good indication of how popular this method is ever going to be, but that's something you could do. And then, once again, radial trajectories are a special case. Ooh, sorry, I'll speed up. So all of these esoteric trajectories pass through the center of K-space, as I've already told you, and where they pass through, you can use those points to estimate motion. One of the UR papers is propeller, because you acquire your K-space in these blades, like the blades of a propeller. The other UR publication is called blade, same idea, and you can derive rotational and shift information from it, and you can turn this into this if you correct for everything that you could. Or if you have some of these sort of golden angle arrangements, that just means that there's an optimal way to stagger like spoke 1, spoke 2, spoke 3, etc., around K-space to get you both temporal and spatial resolution, and you can work out a lot of information from these, but I don't want to go too much in depth. Okay, what are the drawbacks of navigators? They will take time most of the time. They can cause spin history effects. This is not that big of a drawback, because you introduce a secondary effect to get rid of a primary one. It's always worth it, but they will still do that unless it's a FET-nav. And it's not something that a physicist can just bash together in an afternoon. It's a significant MRI physics investment. Let's say you don't want to bother with navigators, you want to use a camera. That's optical tracking. So you have a fairly expensive, almost all plastic camera, because it has to sit either in the bore or it has to have some other properties, which we'll talk about. And you have a marker. This is a Moiré pattern marker. So there's many optical tracking methods. I will talk about the one which I've personally worked with. This is a Moiré pattern marker, which is a cool little thing that allows you to infer 3D motion from a 2D plane. And you can either attach it to the skin, in which case you don't care that much about really high resolution. If you do, then you need something that's rigidly attached to the skull, which means a bite bar. Or you might want to do away with the bite bar or with the marker altogether. These are the markerless optical tracking methods. I'm just mentioning that they exist. I have no experience with them, and they haven't seemed to have taken off that much. But if you have this optical tracking method, then you can correct for motion, let's say in fMRI. This is from my older group in London, or the highest resolution in vivo data sets published, I think, to date, also use optical tracking. So here you can see that a lot of information is lost that is then corrected for using tracking. So the drawbacks of this are it's a significant hardware investment, camera, camera, feedback loop, etc. If you do ultra high field imaging, you do need a bite bar or something similar, because if you do ultra high field, your image resolution should ideally be 500 micron or below. And if you just move the skin here, you can see that there's a lot of motion between my skin and my skull. So you need something that's attached to your skull, which is a bite bar. Patients do not like bite bars. So this is more or less unsuitable for patients. Full stop. Lastly, I want to talk about RF-based tracking. This is when you, for example, have an additional set of small pickup coils that will generate you some signal. And there's, I think, 2 or 3 groups working on this. So these are additional RF probes, and you can improve your image quality using that. There's ways to play around with the, Another thing is the pilot tone. Here you have a tone, a RF generator that just generates your signal well outside your field of view of interest, but within the twice oversampled frequency domain. And that can tell you the respiration state. Or this is something that Aaron Hassan-I did, which is a PTX call, and then the scattering parameters of it will once again tell you about, in this case, respiration. Any questions, or should I speed up? No questions, now speed up. Okay. Now we have our motion data. Let's do something with it. There's two competing ways to do it. One is the prospective motion correction, which is just this. You have your MRI scanner, you have something that tracks the motion in the MRI scanner, and then while the motion occurs, in this case a rotation, you effectively rotate the field of view. You adjust your MRI while you're acquiring it to counteract the effect of the motion. And once again, as far as I know, and that's their claim in the paper, is the highest resolution in vivo human data acquired so far has been using that, for the simple reason that if you do 300 micron isotropic resolution, then the simple fact of people just breathing will induce motions on the same level. So you need something to counteract it. And I'd say it looks quite good. Or you can do something retrospectively, in which case you have your data, you have your motion trajectory, and then you do something afterwards with it. You can do this in k-space or in image space. And one way to think about retrospective motion correction is that the co-registration and outlier rejection that you do for basically all of fMRI is retrospective motion correction. You're just counteracting the bulk motion of people's heads between EPI volumes, and you say that, oh, you know, if one volume has been acquired in this state and it's too big of a motion, you just reject it. That's the same idea. You can do something that's rejection and reacquisition. So, for example, you acquire all of your data, you figure out which k-space lines are corrupted, and then you reacquire them, which is what my method did. I hope you see some improvement in the image quality. There should be some, but most of the time this is combined with the reconstruction, because if you're messing around with k-space and reconstructions, you might as well correct your k-space before you reconstruct, or in an iterative process. This is from the very nice disorder paper, this data here. So this is the same k-space data reconstructed with motion and then with motion correction. There's a special case for retrospective, which is autofocusing. It's not that much used, but I think it's a cool idea. The idea there is basically that for each sort of patch of your image, there should be a image metric that tells you it's as sharp as it can be. And then you take this patch, you transform it into k-space, you apply some motion trajectory to it, you transform it back, you look at this metric, is it sharper? Yes, then you keep that motion trajectory, you enlarge your patch, and go on, go on, go on, go on, go on. The reason, again, these haven't taken over the world is that this can become incredibly computationally expensive really fast, because you have increasing patch sizes, you have arbitrary motion trajectories to try out, and you have to do effectively non-uniform Fourier transformations there and back, there and back, there and back. So it's a cool idea, but it has massive limitations. Okay, so you have retrospective and prospective. What are its pros and cons? Prospective will not give you any loss of data. There will be no k-space energy rotated out of your field of view, but you need something that has a sub-TR latency from acquiring whatever navigational data you had to updating your field of view. which if you're doing, let's say, flash imaging is 25 milliseconds, that's a lot to ask of any system. So that's a pretty big drawback, but when they work well, they work well. Retrospective is not sensitive to latency. It is sort of incorporating a loss of data as a sort of taken that, the case-based energy that has been rotated out of your acquisition is just gone, or equivalent ideas, and it can be very computationally expensive. Any questions here, or should I just barrel through the last 5 minutes? I'll barrel through. Okay, connections to deep learning. This is completely outside of my field of expertise. I just took one of the most recent deep learning motion correction publications and looked at their reference list. It has been used to detect motion. So this is sort of showing which patches are most likely to have motion based on a deep learning algorithm. And this is showing you how they generated the motion corrupted data. It's a fairly cool idea, as you take one frame and then you put one frame, one line, and you put it somewhere else. It's going to be motion corrupted if you talk about like cardiac imaging. It has been used to correct for motion as well. I am fairly skeptical about sort of deep learning magicking back data where there wasn't any, but it is a field. We have in the lab connections to deep learning. So I just mentioned that this is a thing that exists. We might be able to start something with it. Okay, let's just put the questions to the end. There's a lot of topics I didn't cover, and I'm sorry about that. So I didn't compare these in terms of sensitivity, their resolution, etc. I didn't talk about KT methods, radial subsampling magic, compressed sensing, etc. This is a field of acquisition techniques that acquire sort of 4D data, so both spatial and temporal, and then you have correlations in space and in time, and you can use these to figure out your motion, do motion corrections. It's cool, but I have no time to cover them. I didn't talk about breathing baths and ECGs. I didn't really tell you anything about non-neuro stuff. I didn't mention scanner vibrations, which are, if you're doing high resolution diffusion, pretty important, because your diffusion will vibrate the table, and as the table vibrates, the head vibrates, and as the head vibrates, your encodings are off. So that's something to take into account. There's a couple of really good papers on it. I didn't go all that in depth into retrospective or prospective, to be honest. I don't think I mentioned at all what you do with the non-rigid transformations. All of these sort of assume that the thing you're imaging is rigid, at least at the time you're acquiring it. And I'm sure I forgot something else that I forgot. So apologies for that. If you want to learn more, there's 3 good reviews that I leaned on quite heavily. They seem to all come out from more or less the same group, like Zaitsev, Speck, Zaitsev again. This isn't because I think they're the fount of unlimited wisdom. These are just relatively good reviews, and either their references or things that reference them are a good sort of jumping off point for getting into this whole topic. And with that, I'd like to end my whole thing with a summary that's taken from one of their titles, which is that motion in MRI is a complex problem with many partial solutions. And with that, I'm done, and I await all of your questions if you're happy to stay a bit over time.